Hi, my name is Shadrach Hepner, and I'd like to talk to you about the work I'm doing at the Plasmadynamics and Electric Propulsion Laboratory. If you'll start with me in the top left panel, my work involves these devices called magnetic nozzles. These can be divided into two primary components. First, we have some upstream ionization source that generates a plasma from a neutral gas input. Commonly, these involve radio frequency or microwave antennas, as we see here. The second component is the applied magnetic field, which confines the plasma and allows it to expand downstream. This expansion converts thermal electron energy into directed ion energy, generating thrust. While these devices do not yet operate in space, they maintain several benefits over other common systems. Primarily, they are known to be able to operate for extremely long durations. This is mainly because of the fact that the magnetic fields are roughly parallel to the walls inside the discharge chamber, reducing wall transport and also erosion. They are also largely propellant ambivalent, implying that they are optimal for missions requiring in situ resource utilization, such as refueling during the mission. Now, moving down to the bottom left panel, the specific problem I'm trying to solve is that of electron cross-field transport. While positive ions are often too massive to be affected by the magnetic field directly, electrons are much lighter and tend to adhere to the field lines much more closely. If no cross-field transport mechanism is in place, the electrons will follow the field lines entirely around, returning to the spacecraft at the end, inducing charging effects that will not only interfere with any equipment that's on board, but will also pull the ions back as well. This will completely negate thrust. And even in the less extreme case, as electrons diverge farther than the ions, the charge separation between the two will induce a radial electric field that will diverge the ions as well. This radial momentum is an inherent efficiency loss that will want to be mitigated. Moving now up to the top right panel, I am specifically investigating the impact of drift-driven instabilities on this process. These instabilities have been shown in a wide array of plasmas to induce cross-field electron transport, and it stands to reason that they may influence nozzle dynamics as well. As electrons expand through this nozzle, they develop motion not only in the radial and axial directions, but also they interact with the magnetic field and develop an azimuthal motion as well. This process is generally an unstable situation, and so a variety of so-called drift-driven instabilities may develop. As these instabilities form, they derive their energy from the electrons and induce a drag on their motion that can push them off of the field lines. My investigation so far has revealed a certain instability known as the lower hybrid drift instability. Now moving on to the final panel in the bottom right, our measurements so far have determined that this wave likely contribute significantly more than other classical mechanisms. In fact, in this image, we see a two-dimensional map of the Hall parameter throughout the plume of the thruster as measured by a suite of electrostatic probes. This Hall parameter can be understood as a relative measure of confinement of electrons to the field lines. And we can see here that the effects of the wave are indeed much more significant than classical effects. This can be seen in the fact that the Hall parameter induced by the waves is several orders of magnitude lower than that induced by classical effects. Now, while this relative measure is definitely important and a significant milestone in this work, our work is ongoing to quantify this more thoroughly and determine exactly how the electrons are interacting with the magnetic field throughout the plume, involving direct measurements of the electron trajectories. Thank you for listening.